Assalamualaikum. Hi everyone. So what we're gonna do today is I simply gonna continue with what we have discussed previously. So in our previous discussion, we have basically looked at the concept of how we apply the first derivative, and then how we apply the second derivative. And in doing so, we have basically used them to identify local extremum, either a local maximum or a local minimum. I mean, the highest point within the neighborhood, okay, of a function, as well as the lowest point within a closed neighborhood, okay, within the certain domain, or within the certain interval that's given to us. Now, inshallah, this time we're gonna expand the concept a bit from local extremum. We're gonna look at the concept of absolute extremum. I mean, the difference is very simple. Local means we only compare the value of f of x within that locality, within that closed neighborhood, okay? While for absolute extremum, we are comparing that point with all the points along a specific interval. So that's why it becomes absolute, either the highest or the lowest point within that the interval that is given to us. Okay, so let me just open the slides. Okay, so I hope everyone should be able to see the slides. Okay, so we're gonna basically discuss this concept of absolute maxima and absolute minima. Okay, so from our previous discussion, okay, we have basically defined local maximum and local minimum. So if we have a function, okay, f at this point c, okay, at any real point, any real number c, it will be a local maximum if the value of the function at c is higher than or equal to all other x's, okay, for all x near c, while it is a local minimum if f of c is lowest, okay, it is smallest or equal to all the function of for all other x near c. Okay, so basically what we're going to do now, we're going to basically try to identify, or we try to find the largest and the smallest values of f of x throughout the domain of f. So this will then bring us to the definition of absolute maxima and minima. So if we have f of c, okay, the value of our function at c is greater than or equal to the value of our function for all x within the domain of f. Okay, so basically this means this is the highest point. Then compared to all other x's, then f of c is called the absolute maximum of f. And similarly, the opposite is true. If f of c is lower than or equal to f of x for all other x's within the domain of f, then f of c would be the absolute minimum of f. Okay, so an absolute maximum or absolute minimum, okay, is called an absolute extremum. Okay, an absolute extremum. Now, this is just to visualize the example of absolute extremum. Okay, so this is a cubic function that we have basically met before, right? A cubic function, n shape. Now, if you look at this graph, can you identify any local maximum? Okay, so we have a kind of within a certain locality, we may have a local maximum over here. But if we want to find the absolute maximum, is that the highest point? Okay, so without any domain or any range that is without any domain that is being specified to us, any interval, we may not be able to identify the absolute maximum yet. Okay, In this graph, basically, the function f of x has no absolute maximum or minimum. Okay, why? Because there is no point which is highest than or lowest than all other x's. As you can see, this point, for example, is it the highest? No, it is not the highest because the f of x here is lower than the f of x over here, right? I mean, this graph going to continue further up. So, I mean, this graph doesn't have any absolute maximum or absolute minimum because this is not the lowest point. Okay? It is not the lowest point. However, this graph have local maximum at x equals -2 because within this locality, this is the highest point. Okay, this would be the highest point. And we have a local minimum here where this is the lowest point compared to all other x's within this neighborhood. Okay, within this neighborhood. So I hope by looking at this example, you should be able to distinguish between local extremum and absolute extremum. Okay, second example, in this case, we have a quadratic function fx equals 4 minus x squared. Okay, now it has a local maximum, right? This is the highest point within this locality at x equals 0. At x equals 0, our f of x is the highest. Okay, is the highest. And this local maximum is also an absolute maximum because this is the highest point compared to all other x's. This is the highest. Okay, so f of 0 when x equals 0 is highest. The highest than all other x's, right? So this is also our absolute maximum. Okay. Now, does this graph have an absolute minimum? No. We don't have any absolute minimum and we don't have any local minimum as well because the graph is continuously going down. So we cannot find the lowest point. Okay. Next example. Now, by looking at this graph, okay, f of x equals x to the power of 2 over 3. Now, does this graph has an absolute maximum? Okay, or local maximum? Local max? No. What about, so when we don't have local max, surely we don't have, so no absolute max. Isn't it? I mean, if we don't even have a local maximum, how can we have an absolute maximum? What about minimum? Is there a local minimum? Yes, right? This is the lowest. When x equals 0, so f of 0 seems to be lower than all other x's. So this is our local maximum. Sorry, local minimum. Local minimum. And within this whole domain, the whole domain of the graph, which is from negative infinity to positive infinity, this is also the absolute minimum. Okay, the absolute minimum. Okay, so this brings us to theorem 1, the extreme value theorem, which basically says that a function f, okay, which is, first of all, we have to make sure that it is continuous on a closed interval AB. Okay, so in the previous examples, we basically look at the whole domain of the graph from negative infinity to positive infinity. Now, the extreme value theorem make our life easier by limiting the domain. If let's say we are given a closed interval with the starting point A to the end point B. So these are the two terminal or end points of the interval A and B. Now, this function, if it is continuous, for sure, we know that there must be an absolute maximum and an absolute minimum within this interval. So within this interval, surely there must be a point where the graph is the highest or the lowest since it is continuous. Okay, so let's have a look at this example. So we have a polynomial function to the degree 3. It's a cubic function, x to the power of 3 minus 21x squared plus 135x minus 170 on the closed interval from 2 to 12. Okay, So first of all, we need to basically make sure that this graph, is it continuous? Yes, we know. Since this is a polynomial function, it would be defined throughout the domain from negative infinity to positive infinity. So for sure, the graph is continuous from 2 to 12. Within this closed interval, it is continuous. Now, let's try to draw this graph. So this is how we draw the graph. So it is a cubic function, again, a kind of an N shape, okay, N shape, where we start from 2, because this will be the focus of our analysis. We simply going to focus our attention within this interval from 2 to 12. Now the graph is continuous. We don't have to lift, okay, our pencil. Now, is there any absolute maximum? Okay, is this an absolute maximum? No, because within this interval, this point is not the highest. We have all other points here, which is the highest. So surely now, within this interval, this would be the highest point, isn't it? The highest point. Okay, so this is why, okay, the absolute maximum for this function within this interval occurs at this endpoint, 2 and 12, where f of 2, okay, sorry, f of 12 is the highest. Then all other x's within this interval from 2 to 12. Okay, from 2 to 12, this will be the highest point. Hence, it is the absolute maximum. And we have absolute minimum at this endpoint. At this endpoint, because this is the lowest. Okay, the lowest. Okay, within this interval. As we move on, let's say what happens when we change, we make the interval to be smaller. Instead of 2 to 12, now we make it smaller to 4 to 10. Now, from 4 to 10, this is now would be the focus of our analysis. Okay, the focus of our analysis. It has become smaller. So we no longer, we got now exclude these tails, the both tails on left and right. Now, when we focus on this graph, okay, within this interval, now this would be the highest point. Okay, so this is the absolute maximum which occur at f of 5. Okay, f of 5. And the absolute minimum would be here, because when we compare, this is the lowest point. Okay, throughout this graph, this would be the lowest point within this interval. Okay, from 4 to 10. Okay, now what happens when we change? We make it smaller. As we make the domain, okay, of the function to be smaller, okay, so we make the interval to 4, from 4 to 8. So now we have truncated, okay, we have cut off the tail on the right further. So our absolute maximum is still here. Okay, this is still the highest point, but now the lowest point, the absolute minimum, will be right at this end point. At this end point, when we evaluate at f of 8, okay, at the end point. Okay, now what if we change the interval from 3 to 11. So from 3 to 11, okay, you should be able to see that now we have 2 points. 2 points that are of the same height and 2 points that are of the same low. Okay, I mean they have the same f of 5 equals to f of 11, which is 105. Okay, so in this example, our graph within this specific interval, we have two absolute maximum. Okay, so maxima is the plural. So the absolute maxima for the function f of x within this interval 3 to 11 occurs at x equals 5 and x equals 11. Okay, so it is possible for us to have more than one absolute extremum. Okay, as long as the graph is continuous, as long as the function is continuous within that interval. And similarly, we have two absolute minimum. Okay, two absolute minimum, two absolute minima, which occur at x equals 3 and x equals 9. Okay. Now, this basically then, give us the second theorem. where how to locate the absolute extrema. So absolute extrema, if they exist, they must occur at critical numbers or at endpoints. So there are two candidates. So there are two places where we need to find, where we need to investigate. If we want to find the absolute extrema, so they must occur at either the critical numbers, to remember the critical numbers, right? Critical numbers, or at the endpoints. Okay, or at the endpoints, like at the this endpoint. Okay, the endpoint. They might be they are the candidates for either the highest or the lowest point. So this is the procedure to find absolute extrema on a closed interval. Step number one, we have to make sure it is continuous. Step number two, we have to find the critical numbers. Step number three, then we have to evaluate f, the value of f of x, the function itself. Okay, so what we need to do is that we simply replace all these x's with the critical numbers that we found in step 2, as well as the endpoints a and b. Okay, a and b. So we replace this a, b, okay, into these x's, and then we replace the critical numbers that we have found in step 2. And then we simply compare. For step number 4, to find the absolute maximum, we compare all the f. So f of when x equals a, f of when x equals b, f when x equals to, let's say we found two critical points, right? F equals C2. So just list them out, compare. So the largest value would give us the absolute maximum, while the smallest value would give us the absolute minimum. Okay, from step 3. Simple, right? Should be simple. Okay, so let's have a look at this example. So let's say we have this function, okay, a cubic function, x to the power of 3 minus 6x squared, on this interval, -7 and 7. So step number 1, we need to check whether this function, polynomial function, is continuous. Yes, this is a polynomial function, right? I mean, so the function is continuous and defined throughout this range from -7 to 7. Okay, so step number 1, done. It is continuous. Now, step number 2. What is step number 2? We simply need to find the critical numbers, right? So the critical numbers, we find the derivative. So this will give us 3x squared minus 12x. And this, we can factorize this, okay, into 3x minus 4. So we know that, so 3x equals 0, x minus 4 equals 0. So x equals 0. So this is our critical point number 1. And we know here x equals 4. So this is our critical point, critical number 2, C1 and C2. So now this then bring us to step 3. We need to evaluate the f of x at the endpoint. So what we need to do is, so first we do for the endpoints, right? So the endpoints, simply replace. Okay, let me see here. I think there is a typo here. Let me just check this quickly. See what happens when we have square cube minus 6 -1 -7. Okay, so there's a typo here. So this would be from -1. Okay, so please make the correction. The interval given is from -1 to 7. So when we replace -1 into our x, so first thing, so we take the endpoint. So f of -1 give us -7. And then f of, okay, why am I writing? Okay, it's because you're gonna have it. You will have it here. Okay. So and then next one we simply, so this is, we replace with the endpoint. So this is our endpoint. Endpoint -1. Next step, okay, replace this with the first critical value, C1. So we replace x here with 0. So 0 to the power of 3 minus 602, so give us 0. And then our second critical number, 4. So 4 cubed minus 6 multiplied with 4 square, which will give us -32. And finally, we have This is again another typo. So when we replace 7 here, 7 to the power of 3 minus 6 to the power of x2, this should give us 49. Okay, 49, not 9. So this is n point 7. Okay, so when we compare these four values, so the smallest would be negative 32 and the largest is 49. So within this interval, we know that this is our absolute minimum and this is our absolute maximum. Okay, right? So this is what we have found. So this would be the answer. Absolute maximum of the function is 49 when x equals 7, and the absolute minimum is negative 32 when x equals 4. This would happen at the end point, the right end point, and this would happen at the second critical number that we have found from step 2. Okay, so I hope the example, have you should be able to find, to locate the absolute extrema easily. Okay, because it is very simple. It is not that complicated. You just need to compare the values. Okay, so next one is simply a kind of repetition, just to review the application of second derivative, because the second derivative would be able to assist us to identify or to locate the absolute extrema. Okay, the extrema. Okay, so we know that at the critical, okay, at any critical number, okay, that we have found, the slope, okay, of the tangent line at the critical number that we have found would be 0. Okay, would be 0. Now, if we have established this, so this is from the first derivative, right? The first derivative test for any critical number, okay, to be, for any number to be a critical number, the slope of the tangent line at that x must be 0. It must be a horizontal tangent. And let's say we have also found that the second derivative, okay, second derivative of that value, okay, c, or within that neighborhood, is positive. Second derivative positive. If you remember, second derivative positive, so you got money. So this implies concave upward, right? So if we have these two, if we have established from the first derivative is 0, second derivative is positive, so this implies the function is a local minimum. Local minimum. We have a lowest point. Okay, as you can see here, second derivative, this is what we have discussed before, right? I mean, the concave upward means previously the slope, okay, or the first derivative, okay, is negative, and then it changes to positive. So we have a partition point here. The critical number here is the one that basically changed the slope from negative to positive. This is from the second derivative. Okay, and the opposite is true. If we have established that the slope of the critical number is 0, and at the same time the second derivative is negative, okay, so we have concave downward. When we have a concave downward, this implies we have a local maximum. Okay, the highest point. Okay, the critical number that we have found would give us a local maximum, where the function at the value at the critical number c would be the highest within that local neighborhood. Okay, so we can basically then use the second derivative test for local extrema. Okay, so this is the application of second derivative and how it help us to identify the local extrema. So if the second derivative is positive, so we have f of c will be a local minimum, lowest point. Okay, lowest point. Now, if the second derivative is negative, so we have a local maximum, highest point. Okay, so this table would basically summarize the second derivative test. Okay, the second derivative test. So first of all, we need to establish that the slope must be 0, and then then we check the second derivative, either it is positive or negative or 0. Okay, so this would be the conclusion. Okay, the conclusion. So positive second derivative means we have concave upward, which implies a local minimum, right? Positive, positive. This is negative, negative. Local minimum, local maximum. What if our second derivative give us 0? In this case, the second derivative test basically fail. When it fail, we cannot derive any conclusion, and we cannot basically decide whether it is concave upward or concave downward. Okay, but that one will be discussed later. Okay, it will be discussed later. So this give us the third theorem, okay, which is basically define the second derivative test. The second derivative test, if f, okay, so the theorem 3 basically help us to identify the absolute extrema within an interval. Okay, so let's say we have a function which is continuous, okay, on an interval I. So I stands for interval from A to B. So these are the endpoints from A to B. And we have only one critical number C. So there are three conditions basically. Okay, three conditions basically. The function, or two conditions, let's say. So first condition is that f must be continuous within this interval A to B. Second condition is that there is only one critical number within this interval. Then if the slope is 0 and the second derivative is positive, then f of c at this critical number will be the absolute minimum. Positive, positive, absolute. Sorry, it should be a smiling face. Positive, so absolute minimum. Okay, and the opposite is true. If the slope is 0 but the second derivative is negative, then the value, the function at c at this critical number will be the absolute maximum of f on that interval a and b. Okay, from a to b, negative a to b, so we have absolute maximum. So there's only one critical number, right? So that critical number will either be an absolute maximum or absolute minimum. Okay, so let's say we have this example. We have this function, a ratio function. So within this interval from 0 to positive infinity. So this is an open interval on the right hand side. Okay, on the right hand side, it is an open interval. So how do we do this? So we find the first derivative. So what is the first derivative? So we have 1 minus, right? This is 1 and this is x negative 1. So minus 4 divided by x square. Okay, divided by x square. Now, can we expand this? Yes, so this becomes x square minus 4 divided by x square. And we can factorize this, right? So this becomes x minus 2, x plus 2 divided by x square. So what are the critical numbers here? So the critical numbers we have 2. So take note. So this would be A and this would be B. But B is not a real number. B is not a real number. So our critical number, so when we set this set to equal to 0, so we have x equals, so x minus 2 equals 0, x plus 2 equals 0. So in this case, we have x equals 2. This one we have x equal negative 2. So these are the critical numbers. Okay, what about the second derivative? Second derivative, okay, so the second derivative would be, so this is, so I'm just going to use this one because it make it easier, right? Because if we differentiate this, it becomes 0. What about this? So we have negative 4. So this one, the power gonna be added, right? 3. Okay, let me just why am I? Let me just rewrite this. The first derivative would be, this is basically 4x negative 2, right? So the second derivative would give us 0 minus. So negative 4 multiplied with negative 2 plus 8 x to the power of negative 3. So we have 8 over x to the power of 3. Okay. Now, within this interval, 0 and positive infinity, 0 and positive infinity, so we have only one critical number, which is 2. Right? We ignore this because this is outside interval. Because x equals negative 2 is smaller than 0. I mean, if you compare back to this, right? So that's why we have only one critical number, which is 2. Okay, which is 2. So now what we need to do is we want to check, right? From theorem 3, we want to check. So let's see whether we can apply theorem 3 or not. So one of the criteria has been fulfilled. I mean, we know the graph is continuous, right? Within this interval, okay, within this interval except 0, right? I mean, 0 is not. So we start with 0. So all along the right hand side of x, okay, from 0 to infinity, we know x is continuous. F of x is continuous. And there is only one. So when we have only one, so only one critical number, right, which is x equals 2. So now we want to see whether we can apply theorem 3 or not. Okay, theorem 3 or not. So we have to check the value of the second derivative. Right, this one we have already set it equal to 0. Right, the first derivative has been set to 0. So what is the value of the second derivative at this critical point? So the second derivative when x equals 2 is, so 2 cube. So 8, what is 2 cube? It is 8, right? Equals to 1, which is positive. So positive. Second derivative, when it is positive, we have an absolute minimum. Right? Is there any absolute maximum? No, there is no absolute maximum because there is only one critical point. And this critical point at x equals 2, we have already established that it is a minimum. Okay, it is a minimum. Since there is only one critical number, so we also know that this is the lowest point compared to all other f of x. F of 2 is the lowest, and because of that, this would give us the absolute minimum when we apply theorem 3. Okay, um, so I think that's 8. And okay, so that's all for now. Inshallah, when we have time, we're going to discuss other things with regard to the how we can apply all these different concepts, the different theorem from the first derivative and second derivative to assist us in making decisions that are related to business and economy. So thank you and see you next time. Assalamualaikum warahmatullahi wabarakatuh.